Okay. So in the supplementary reading section of some of the reference books, there is a detailed explanation of how Huygens principle can be used to explain each of these phenomena. Okay, so that's for extra reading for the students. But in class, they just need to know that this principle can be used to explain all these three phenomena. In reflection, we have the law of reflection, which simply states that the angle of incidence will be equal to the angle of reflection for a wave that is reflected off a surface. And when we are talking about the angle of incidence and reflection, we are always measuring the angle from the normal. Okay? Refraction, when a wave crosses a medium from one medium to another medium, at the boundary layer here, there is a bend in the wave's direction due to refraction, and this happens when the speed of the wave in medium 1 is different from the speed of the wave in medium 2. Okay? You want to go into a detailed description of why this happens. I'm not going to do that here because it's very well explained on page 24, and all the steps to get this information are on page 24. One thing though that you want to mention, firstly, the law of refraction, which is called Snell's law. Here again you have the angle of incidence, and this here is the angle of refraction. So Snell's law states that the refractive index. Okay, refractive index is in the case of light. So you want to mention that the speed of the wave in medium 1 divided by the speed of the wave in medium 2 is equal to sine of angle I divided by sine of angle R. Okay? When we are talking about the wave being light and medium 1 being vacuum, for example, let's say this is light and it's traveling into another medium 2. So the refractive index of medium 2 would be given by sine of angle I over sine of angle R, which is denoted by N. Okay? So that would be the refractive index. Now, one thing in refraction that you want to mention is, for example, if you have wave fronts which are crossing over from a medium, let's see here. So for example, if you have a boundary layer here and the waves are traveling like this, okay, and after refraction, these are the wave fronts. So remember, the wave fronts are not the direction of travel of the wave. The wave fronts are perpendicular to the direction of travel of the wave. So for example, if a ray was traveling like this is the direction of travel for this wave in this medium, and in this medium the wave is traveling in this direction, again perpendicular to the wave fronts. Okay? So how do you decide which medium was the wave traveling faster in? The frequency remains constant. Okay, the frequency does not change. So we have speed equals lambda f, right? So therefore, the higher the speed, the greater the wavelength for the same frequency. So if the wavelength is greater, the speed of the wave is higher. Therefore, the speed of the wave in medium 1 here is higher than the speed of the wave in medium 2. Okay? Okay. So for example, this could be shallow water and this could be deep water. Therefore ripples in a water tank would travel faster in deep water as compared to traveling in shallow water. So this is one thing that you want to explain. So we have reflection and refraction over here. Now diffraction can be directly explained using Huygens principle. In diffraction, what happens is, like we mentioned, each point on the wave actually acts as a secondary source of the wave. So we mentioned that this happens because of the pattern that we see is because of the interference of these individual sources. Now if we block one segment of the wave here and another segment of the wave here, and we have a small aperture over here which allows the waves to pass through, what we will see is that only this portion of the wave acts as a secondary source of the wave, and the pattern of waves produced would be in this pattern, right? Again, if we remove one section of the barrier over here, then this side of the wave, there is no superposition, so we will continue to have this pattern. But on this side, since the secondary sources are interfering, we will still see the same pattern. Again, the frequency of the waves will not change. Okay, so you want to make sure that they understand that this is happening because there is no interference of the waves on this side. Okay, so for example, if we are talking about water waves and these are boats which have been protected by a protected barrier over here, we will still see the boats rocking even though they are not in direct line of the water waves because of diffraction. Okay, so the next part is about interference. 4.5.5 and 4.5.6 cover superposition and interference. So the 4.5.5 is the principle of superposition. You need to make sure that the students have pretty much, they should be able to memorize the definition over here, because a lot of exam questions for waves ask them to state the principle of superposition. And of course they should be familiar with what the principle of superposition is from IGCSE. The interference pattern produced on page 28 is from 2 point sources. So you can see that along the dotted lines on this diagram, you have the crest of S1 meeting the crest of S2, and also the troughs of S1 meeting the troughs of S2. Such a line will have a maximum amplitude of oscillation. So these lines are called antinodes. Whereas the solid lines, what happens is that the crest of S1 meets the trough of S2, and the trough of S1 meets the crest of S2. So therefore you have destructive interference happening along those lines, and there is no amplitude. Those lines are called modes. So the end result is a pattern that you see on this diagram over here, and you will not see the individual waves being produced. So this pattern is called the interference pattern, and in order for this interference to occur, you must have the two sources being coherent. Okay, so another thing you want to mention, coherent sources. So in order for two sources to be coherent, you must have that they have the same frequencies and that they are in phase. Okay? In some exam questions, especially MCQs, I have noticed that both of these conditions can be met by one phrase or one condition, that the two waves have a constant phase difference. Okay? So either these two or this is sufficient for the two sources to be coherent. Okay? And then the last part over here is talking about path difference and how. Okay, so in order for two waves to produce constructive interference from 2 point sources S1 and S2, okay, if the paths are exactly the same, okay, if the paths are the same, S1P and S2P. If S1P is equal to S2P, we would have constructive interference at this point. Okay? Why? Because the path difference is 0. Okay? But for example, a point here, P dash, let's say the path difference between these two paths, S1 P dash and S2 P dash, can be seen if we draw a perpendicular from S1 P dash to S2 P dash. Okay? And this point here, let's call it X. Okay. So S2X is the path difference. Okay? So if the path difference is it's an odd multiple of half of a wavelength, which means lambda over 2, 3 lambda over 2, 5 lambda over 2, that is when we would have destructive interference, because the crest of one wave would meet the trough of another wave. Okay? So this should be either lambda over 2, 3 lambda over 2, 5 lambda over 2, etc., etc. This would give you destructive interference. Alright? And if the path difference is either, if it is 0 or lambda, if the path difference is one wavelength, then again the crest of one wave would meet the crest of the second wave. The crest of the first wave would meet the second wave's crest. If the path difference is either 0 or lambda or 2 lambda, so as long as it's an integral multiple of lambda, you would have constructive interference.